Good afternoon, everyone. First of all, I apologize for being late. Apparently, pointers in C++ lead to people arriving late all over the world. I'm going to have a very short talk on behalf of Zedong Peng, who is a postdoc in my group, who unfortunately, for reasons which I'll tell you over dinner, couldn't attend today. So this presentation is a short show on how have we been leveraging all the infrastructure that Pedro just described in order to get some interesting results for optimization. And in a very short summary, how to make Gurobi 20% better. So let me show you what we did. I don't need to tell you much about quadratic unconstrained binary optimization. I think Pedro has done an excellent job covering this kind of optimization problem, quadratic, no constraints, binary variables only. It has a number of applications per se, and in particular in physics, people like it a lot because it looks a lot like the Ising model, which is interesting from a statistical mechanics point of view, but also because people developing hardware particularly fitted to address this problem have the facility of finding like a physical equivalent to it, right? And people are building all these devices. Pedro might have told you about the stuff that folks are working on in Microsoft using photonics, and some other people are even using computers that leverage quantum mechanics for this, or quantum computers, in particular quantum annealers. So there are several methods out there to address QUBO problems, quadratic unconstrained binary optimization problems. Some of them are very familiar to what we are used to from a traditional mathematical programming community. So we have exact algorithms based on branch and prune, branch and price, branch and check, with all the battery of methods that I would say commercial MIP solvers have available. Commercial and open source MIP solvers have available. There are a number of algorithms that have been particularly designed for this problem. So among them, simulated annealing, taboo search, local search, evolutionary algorithms. Many of them have been sort of conglomerated into a single study that people, in an excellent paper by Dunning, Gupta, and Silverhorst, which is called like what works best, and they went ahead and implemented like tens of these heuristic algorithms into something called the MQLib. And finally, well, for quantum methods, we care a lot about quantum methods. I can tell you that at least there are two big algorithms that can address quadratic unconstrained binary optimization using quantum computing. One of them is implemented into gate-based computers, which people call the quantum alternating optimization ansatz, or the quantum approximate optimization algorithm, QAOA, which for the sake of time I will not explain, but feel free to ask me about it. And another one called quantum annealing, for which a Canadian company called DWave has built these particular devices which can solve up to 5,000 variable problems, quadratic unconstrained binary optimization problems, leveraging phenomena explained through quantum mechanics. So anyway, our goal was we want to solve these problems to global optimality. And on one hand, we had branch and bound methods, classical optimization methods, which would provide us with these guarantees to address these problems to global optimality. On the other hand, we had like these very cool, very interesting heuristics, which unfortunately, as the name is already telling you, cannot give us the convergence guarantees to global optimality. So the issue here is how do we combine these two? And so here I'm putting a couple of the companies that put together the solution method. So basically, Gurobi is the solver that we're going to use here as our benchmark, and how can we turn it better using potentially quantum annealers from DWave, okay? And for this, we needed a lot of software, we needed a great platform, and we needed obviously like a programming language and an algebraic modeling language that would help us support this kind of integration. So we found in JuMP, and in particular in QUBO.jl, all the tools that we needed to perform these experiments. So basically, what we are going to do here is we're going to inject solutions or solution information to Gurobi, right? And here there is this tiny diagram explaining more or less how Gurobi, the branch and cut method inside of Gurobi. So one of the methods that we're going to do is that we're going to initialize the problem. if we already have a solution to the original problem, well, how about if we just pass it? Hopefully that will reduce the search that is going to be performed at the branch and cut method, and this would eventually basically increase the performance of the solver, right? The second one, oops, anyway, you can see now the two next one. One is a heuristic callback. So at every node of the branch and cut tree, we can query some solution of that relaxation of the problem, and then hopefully inform it on ways how to improve basically the bounds that it's found so far. And finally, we can give hints on the variables. We can pass hints, for example, on the branching priority. So let's use these 3 steps to make Gurobi better. Sounds good? So here in this particular case, we're going to use a quantum processing unit solver, a QPU solver. And yeah, basically, here the message is that the problems that these quantum machines can solve, at least the algorithms that have been told there, using them raw or just the vanilla version of them, they require 1 qubit per variable, per binary variable in our problem. So we're sort of limited by the size that is given by these devices. So anyway, let me show you, let me just cut to the chase because I don't have much time. We're going to provide the solution at the root, and then we're going to use heuristic callbacks either at each node or after certain conditions have been satisfied. In particular, we care whenever we have dug deep enough into the branch and cut tree such that the subproblems become the size that you can solve on a quantum annealing method. Okay? So anyway, there is another teeny tiny problem here which has to do with the way that these computers are solved. And it's basically that the computers don't have arbitrary connections between their qubits. That means that if you want to solve an arbitrary problem in them, you need to perform a compilation step that people call embedding. And here's an example. Your problem looks like a triangle, your computers look like a square, so you basically need to use 2 of the qubits of your computer to represent a single variable in order to have all the connections that you have there. Well, this sets a big, big limitation into the quantum annealing hardware that exists out there. Although it has 5,000 qubits, the largest fully connected problem that it can solve is of size 164. So, but this also helps us think, how can we better inform the solutions inside of the solver? So the intuition here is that, how about if we start branching by the most connected variables? That should basically inform also the relaxation bounds, but in this particular case, it's also super duper helpful because the subproblems that arise have better chances to be embedded, even if even if the connectivity of the hardware is not given. So this is what we were doing from a software point of view. We're taking, Pedro is very humble, and he might have not told you that he's also developed a benchmark library for QUBOs, right, called QUBOLib, and use his other analysis code QUBO tools to get some data out there. Then eventually we build the QUBO models using JuMP. We call Gurobi there, and we have graph.jl telling us how to set up the branch priority, and eventually all the packages through the QUBO drivers that Pedro was describing, we're calling either the MQLib classical solvers or the DWave quantum annealing solvers. Anyway, these are the instances that we're solving, many of them coming from the statistical physics community, sort of biased towards very dense instances, rather small. Anyway, the baseline is Gurobi. We have this performance index. We do care whether we reduce the number of nodes that it visits and the solution time overall that it takes to solve the problem. We're going to try 16 different heuristics from MQLib, simulated annealing as implemented by the people at DWave, and quantum annealing, which is using this Advantage 4.1 hardware, which, again, I told you, 5,000 qubits, 40,000 couplers or connections between them. Anyway, so first, just by setting the branching priority for these QUBOs to be following the order of the connectivity of the graph induced by the Q matrix, right? In QUBO, we have minimize X transpose QX, and that Q matrix is basically the incidence matrix of a graph. If you go there and compute degrees of each one of those nodes and set those as the branch priority, boom, you already reduce the number of nodes by 22% and the solution time in 16% to prove global optimality on these instances. Now, then we went ahead and we started using the classical heuristics, right? Let's first feed the best solution that these heuristics can find. That's what I referred to here in top 1. And here you can see that in the best case scenario with the best heuristic, we still reduce the number of nodes by 15%, the solution time by 12%. And an interesting experiment that we wanted to do, what if we provided the optimal solution to each one of the problems? Like how much, what is like the upper bounding performance that we can reach? If we had access to this like godlike oracle that would tell us the solution at the beginning, obviously that would reduce drastically the number of nodes and time, right? 95 and 96%. Anyway, and the other part, the other tiny experiment that we did is, how about if you just call a heuristic at every node, right? I mean, you're just putting all the work there, and certainly that doesn't pay off. Obviously, the increase in time, time is out. Okay, what if you eventually add a quantum annealer to this? You can reduce basically by 17 and 12% the number of nodes and the amount of time. And this is feeding either 1, 10, 30, or 100 solutions that is found by these methods, because they excel at giving you a very broad variety of solutions very efficiently. This is in 2 milliseconds. So without further ado, I thank you so much for your attention. And well, I'm so sorry I missed the earlier part of the conference. I hope the rest is as good as you have been. Well, I wish we have as much fun as you have been having so far. Thank you.